Welcome back to the deep dive. Today, we're staring about 56 million light years away at a galaxy that, well, it looks deceptively tranquil. It's called NGC 4102. When you look at the new observational data, you just see this stunning, delicate spiral structure. It's almost serene. But our mission today is to cut through that calm facade because our source material reveals a quietly powerful active secret right in the galaxy's core.
A supermassive black hole.
Exactly. But this isn't one of those flashy, hyper-violent cosmic monsters. NGC 4102 is defined by its subdued activity, which is still highly significant. We need to understand how this particular kind of quiet giant operates, why it's so difficult to see, and what two strange astronomical classifications are essential to describing it. Think of this as your shortcut to the hidden mechanics of galactic evolution. And just for context, you can find NGC 4102 shining faintly in the northern constellation Ursa Major.
Otherwise known as the Great Bear.
That's the one.
And that reference point is crucial, because its proximity is exactly why NGC 4102 is such a valuable target.
So it's close.
At only 56 million light years, it's close enough to be an ideal local laboratory for studying these things, these active galactic nuclei, or AGNs.
Yeah, right.
We're not just admiring the pretty spiral arms. We are trying to look past that surface to understand the intricate dynamics between the core and the galaxy it lives in.
Okay, let's unpack this immediately. We know there's a supermassive black hole fueling an AGN at its heart. When we say supermassive, what are we talking about here?
We're talking about a monster. The one dominating this region holds millions to maybe even a billion times the mass of our sun. The scale is just immense.
Even if its activity is, as you said, reserved.
Exactly. The sheer mass is one thing, but the key mechanism here is the active part of AGN. It's the power source.
And that energy doesn't come from the black hole itself, right? It's from the feeding process.
Precisely. This massive gravitational force pulls nearby gas inward, and as that gas spirals toward the event horizon, it accelerates, it heats up to extreme temperatures.
And it glows.
It glows with staggering amounts of radiation. It's the friction and heat of the gas being devoured that generates the light we see, or sometimes don't see. And that radiation spans the entire spectrum, from high-energy X-rays all the way down to radio waves.
Okay.
Now, what's fascinating here is that NGC 4102 doesn't look like the AGNs we often see in documentaries. The hyperluminous quasars that launch these powerful jets of charged particles.
Yeah, the really dramatic ones.
Right. This galaxy is part of the quieter, more subdued group. It gathers gas much more slowly, and that results in a significantly softer glow.
So it's the difference between a roaring jet engine and a smoothly purring generator.
I love that comparison. That's a perfect way to put it.
But that quiet glow, combined with the fact that the core is wrapped in a literal curtain of thick gas, that must make observation an absolute nightmare.
It does. And it seems astronomers have had to develop some really specific, almost counterintuitive technical terms just to classify this kind of hidden low-power activity.
What are these unusual classifications they use?
That's where the language of astrophysics gets highly descriptive.
Yeah.
But, well, simultaneously cryptic. Because this activity is so obscured and so subdued, we need two separate specialized terms to really define what's going on in NGC 4102's core.
Okay.
The first categorization is the one related to that gas curtain you mentioned. It's called Compton thick.
Compton thick? That sounds incredibly dense.
It is. Think of that surrounding cloud of gas as miles of incredibly dense fog. It's so thick, so opaque, that it absorbs the vast majority of the high-energy radiation, specifically the hard X-rays that the feeding black hole is producing.
Ah, so the very thing that would normally be the brightest signal, it's just getting blocked.
Completely blocked.
Yeah.
Most AGNs glow brightest in hard X-rays, but here the density is so high that the photons collide with electrons in the gas, a process called Compton scattering, and they're effectively absorbed or scattered away.
So we aren't seeing the power source directly. We're just detecting the weak signals that manage to leak out around the edges.
Or reflect off the inner wall of that gas torus. You're not seeing the power. You're seeing the shadow of the power.
That's an amazing way to think about it.
And that Compton thick designation, it immediately tells astronomers, okay, we can't study this object primarily in high-energy X-rays. We have to look for that soft, multi-wavelength glow that somehow penetrates the curtain.
So that addresses the shroud. What about the second term? The one that sounds like an acronym generated by a 1980s mainframe liner.
Ah, liner, yes.
What is a liner telling us about the black holes? I guess it's operational profile.
Right. So LINER stands for Low-Ionization Nuclear Emission-Line region.
That's a mouthful.
It is. But the second classification is purely diagnostic. It tells us about the state and the temperature of the gas that we can detect leaking out.
Okay, so what state is it in?
When astronomers analyze the light spectrum from a liner galaxy, they see specific emission lines from elements that are only weakly ionized. This is a critical signature
Why is that so important?
because it tells us that the accretion process, the feeding, is relatively gentle. It confirms the subdued nature of the engine. The supermassive black hole is just gradually drawing in gas from its surroundings. It's not violently ripping it apart.
So it's sipping, not gulping.
Exactly. There are no massive streams of material crashing into the disk at immense speeds. It's a much calmer process.
So if we combine the two classifications, Compton thick and liner, we get a really complex portrait.
You do.
We have a powerful engine, millions of solar masses strong, but it's hidden behind a thick, dense shroud. And that engine is operating at a consistently low, gradual power level. It's a very specific operational mode.
Precisely. And this is why these classifications are so vital for researchers. They're astronomical shortcuts that immediately tell us the mechanism, the environment, and the likely power source of a galaxy.
And without them, you'd be flying blind.
Completely.
Mm-hmm.
We can't just assume all black holes are these ravenous, explosive quasars.
Yeah.
Many, maybe most, are operating in this low-energy, highly shrouded state. And if we miss them, we miss a huge chunk of cosmic history.
That shift from violent consumption to a quiet, gradual glow, it almost feels counterintuitive. Does that reserved nature make it harder to definitively link the AGN activity to observable changes in the galaxy itself?
That's a very important question. I mean, if the influence is so gentle and gradual, isn't there a risk that we might over-attribute changes in star formation, for instance, to the AGN when it could just be normal evolution?
Right.
It's a significant challenge. But by studying nearby examples like NGC 4102, we can measure the gentle outflow of energy and its effect on the gas reservoirs much more precisely.
So it's a low burn.
It's a slow burn.
Yeah.
Unlike a quasar, which can just wipe out a galaxy's star-forming gas in a single huge burst, a liner provides this constant low-level energy drizzle. And we know that even a low level of radiation over millions of years can subtly inhibit star formation or reorganize gas clouds. So the quiet giant might not be destructive, but it is certainly manipulative.
Guiding the slow evolution of its host galaxy over cosmic time.
That's the idea.
Okay, so to see this quiet manipulation, especially through that dense gas curtain, it must require some exceptional instrumentation. We mentioned that this new data is much clearer than previous images.
Yes, the visual information from Hubble is spectacular. You get the beautiful spiral arms, the overall structure. That's all necessary context.
But to look through that Compton-thick shroud, that requires more than just high-resolution visible light, doesn't it? The goal there isn't just clarity, it's penetration.
Absolutely. The visible light is mostly blocked. We need a different kind of eye to see what the black hole is actually doing.
So what's the solution?
Well, what's fascinating here is that this specific study is part of a collaborative project. It intentionally pairs Hubble's visible light imagery with X-ray observations taken by the Chandra X-ray Observatory.
Ah, so that pairing is the key.
That's the key insight. While the dust absorbs visible light, it becomes much more transparent X-rays, especially those reflecting off the surrounding gas.
So Chandra can see what Hubble can't.
It can peer past that dense environment to capture the signature of the black hole, feeding those high-energy photons that leak out or scatter. Without combining Hubble's beautiful structural data with Chandra's penetrating X-ray data, the true nature of this active core would remain, well, completely masked.
So we use Hubble to see the stage, the spiral galaxy structure, and we use Chandra to confirm the actor, the hidden, softly glowing black hole engine, even if that actor is buried under layers of set dressing.
That's a perfect analogy, and it is essential. This is how we prove that the liner activity is indeed driven by an AGN and not some other stellar process like a massive cluster of hot, newly formed stars.
Yeah.
The X-ray signature is the smoking gun. It points directly back to the supermassive black hole.
So what does this all mean? If we synthesize everything we've learned, NGC 4102 is really a crucial nearby cornerstone of complexity. It appears beautiful and simple on the outside, but it houses a quiet, complex, gas-shrouded engine deep within its core. It's our local teaching moment on the Compton-thick liner class of galaxies.
I think the primary takeaway is that NGC 4102 is forcing us to redefine what an active galaxy even looks like. We're moving past the idea that only the brightest, most violent quasars matter.
The quiet giant.
The quiet giant, operating slowly, is just as influential over the long term. Understanding this subdued version is vital because it contributes to our understanding of the full spectrum of black hole behaviors.
We're still shaping their environment.
They are. These low-power engines influence the distribution of gas and the rate of star formation in a persistent, gradual way over billions of years. They are essential drivers of galactic evolution, just in a quieter voice.
It sounds like we should be paying much more attention to the quiet rooms than the loud parties.
We absolutely should. And this leaves us with a final provocative thought to mull over, which circles right back to that Compton-thick shroud.
Okay.
Since the supermassive black hole in NGC 4102 is so effectively hidden, it's Compton-thick, and we needed this painstaking high-resolution X-ray pairing of visible light just to confirm its activity. How many more are out there?
How many other powerful, quieter black holes exist across the universe, currently masked from our view by gas?
Exactly. We might be vastly undercounting the number of active galactic nuclei because they are simply too quiet or too obscured to spot without the specific multi-wavelength approach. There might be a whole universe of quiet, hidden giants out there influencing cosmic structure right under our noses.